So good afternoon everyone. Just comment in the chat box, is the audio and video fine to all of you? I welcome you all back onto the sessions of 𝐂𝐸 2025. So please type in the chat box, is the audio and video fine? It's fine? Okay. Okay. So good afternoon all. So it's fine, right? Yes. So let us start the sessions then. So this is the first Abhyas session. So we have solved a lot of PYQs. So जब PYQ solve करते हैं आपको एक आइडिया आता है कि गेट में PYQs मतलब 𝐂𝐸 एग्जाम में PYQ क्वेश्चंस कैसे आते हैं, करेक्ट? एंड देन once we have thorough with the PYQs, in today's class we thought of solving some new questions. Okay, so we'll have some practice on most expected questions, like because of our experience, like we have dealt this 𝐂𝐸 for so many times. So we have spotted some kind of questions which have high frequency or high chances of coming in GATE examination. Okay, so let us solve those questions in today's class. Okay, and we'll go slow, and if you have any doubt in any concepts and all, please again ask, because this is the last time maybe like for the fluid mechanics I will be seeing you before GATE 2025, and tomorrow Sandeep sir will take the class again. So if you have any questions regarding any things like potential flows or Reynolds transport theorem or things like this, you can ask me. Okay, and secondly, on this same channel we have uploaded the playlist. Okay, so we have created a playlist for GATE 𝐂𝐸 2025 where you have the last year, basically those are the live classes of last year. So we can you can go to the lectures, and if you have any doubt you can revert back in the Telegram channel. Okay, so if you see, this is the schedule that we'll solve with Abhyas. We'll start with the Abhyas session today, and at 7 o'clock Apoop sir will again take the solid mechanics class. Okay, solid mechanics Abhyas of course, and the schedule goes on. So tomorrow Sandeep sir will teach fluid mechanics, and Ramanan sir teaches the solid mechanics part 2 again, and definitely this thermodynamics is by Shivam sir and Vinod sir, and again I'll take the maths. Okay, there's a small slot change for the last class. So this class happens at 9 p.m. Okay, this is at 9 p.m. There is small change in the schedule because of certain clash in the timetable. So the last class will be at 9 p.m. that day. Okay, so 9 to 12. So we will close the preparation for 𝐂𝐸 2025. Meanwhile, if you have any issues, you can always post it in the Telegram channel. Many of our friends are going to this Telegram channel, and we keep solving the questions. Okay, so and if you have any doubts, you can also post in this. The main 𝐂𝐸 का PYQ plus class questions DPP SWT FLT कर रहा हूँ. Is it sufficient? Yeah, definitely. Potential flow आप कवर करेंगे आज. पोटेंशियल फ्लो का क्वेश्चन हम सॉल्व करेंगे, लेकिन जो पोटेंशियल फ्लो का थियरी क्लासेस चाहिए तो मैंने अपलोड किया था ऑलरेडी. ओके, इन द प्लेलिस्ट. ओके, इन द प्लेलिस्ट ऑफ कंटेंट फॉर 𝐂𝐸. सो यू कैन जस्ट go through this lectures. Okay, Rankine over in potential flows is important for 𝐂𝐸 or not? See, potential flows is important and superpositions is really important. Okay, meanwhile I'll just display the notes, my class notes of potential flows, and I'll just go through it very briefly. But in your case, if you want to have a clear-cut understanding, okay, of the of this potential flows, we have already uploaded the videos. Like there will be 5 videos of 2 hours each. Okay, so those are the Parakram batch classes of this time, and we have posted them. Okay, so that it's okay. Like if you want to learn potential flows, you can just go to the content. Okay, chalo, let's solve the questions then. First question, let me display it for you. In the context of study inviscid incompressible flows, consider the superposition of a uniform flow with speed u along the positive x-axis from left to right, and a source of strength A located at the origin. Which one of the following statements is not true? This is not true regarding the location of stagnation point of the resulting flow. So you have a uniform flow plus you also have a source. So this superposition of uniform flow plus a source gives you a Rankine half body, correct? So let's solve this solution. So superposition of a uniform flow plus a source, this gives you the combination of Rankine half body. Okay, so Rankine half body. So once you have this Rankine half body, like maybe I'll just show you the sketching. So you have the uniform flow from left to right with a velocity u, plus there is also a source of strength A actually here. Okay, so this is a source of strength A. So strength A. Okay, and the superposition of these two will give a Rankine half body like this. where you can see maybe this is not very symmetric. So this is how the Rankine half body looks like. Okay, and if you observe carefully, this is the stagnation point. Like the flow, if you draw the resulting streamlines, you'll have the streamlines looking like this. Okay, there is a lot of math in this, again we can see, but as of now I'm giving you the idea. Like this is how a Rankine half body looks like. Okay, and the coordinates of this point, the stagnation point here, is going to be minus m by 2 pi u comma 0. So or minus a, so strength is a here, so minus a divided by 2 pi u comma 0 is the stagnation point if this is the origin. Okay, and this distance is going to be m by 4u, a by 4u, because I have the habit of writing the strength of the source as m, and this maximum width is nothing but a by 2 times of u. Okay, so the full half width is a by u actually. Okay, so normally I'm just giving you the idea, but if you want to see how these things happen, okay, so if you want to see these things, I'll maybe show you in the recently one of the batches, fluid mechanics batches which I have taken. So I'll show you that. Okay, so let's see. Potential flow lectures, yes, so somewhere here, superpositions, not it here, so this, yeah, so you can see I have taught the superpositions. I'll show you in a moment. Yeah, you can see this is the combination of uniform flow plus source. Okay, uniform flow and source of strength, some strength which is m. So what does it give you? So flow past a Rankine half body, this is the superposition, and this is the complex potential function, which if you simplify, you can see a simple analysis gives you this is the streamline. Okay, so this blue one is the streamline corresponding to psi is equal to 0, and the flow which is taking place is how you have. So we calculate the stagnation points and all using some simple understandings of the limit, and this point comes out to be m by 2 pi u. So this length OA is going to be m by 2 pi u. That's how this coordinate is going to be m by 2 pi u, and it has only, or a by 2 pi u minus a by 2 pi u, whatever, and this has only one stagnation point. Okay, and the stagnation point is here. Now let's see what are the options. Okay, it is located, so stagnation point is located left of the origin, correct, because you see if source is located at the origin, then the source will emit flow radially in all the directions. So because of which one uniform flow is coming here, and this source which is here is trying to give the flow in all the radial directions. At this junction, this flow which is going right and the radial flow which is coming from the source, they come to a compromise and you will see a stagnation point. Okay, so it is definitely left to the origin if the source is at origin clearly, and you can see source located at the origin. Okay, so therefore this statement is correct. So you cannot choose this statement because you are looking at not two statements. Okay, then it moves closer to the origin for increasing a while u is held constant. Now tell me one thing, it is given this stagnation point will move close to the origin. Okay, from this you can understand if u is fixed and if a is increasing, so strength is increasing, this point keeps moving away from the origin. Yes or no? If you keep u fixed and if you keep capital A increasing, means the strength of the source increasing, then this point will keep shifting towards left. Yes, because u is fixed, so the flow will try to come at uniform velocity, but the strength of the source has increased, so this source is more capable of pushing back this fluid on this side. Yes, so the stagnation is towards left. Can you all understand this logic? The fluid is trying to come in this direction, but the source at this point becoming strong, so this emits flow, this source emits fluid with a very high velocity, so that the stagnation point means this source is able to control this flow to a much better region, so stagnation shifts left. Here, hence you can see this u is fixed, but a increases, the point shifts back. Okay, you know this. So this statement is actually the wrong statement. It actually moves farther when this is the case. So this can be taken as the correct choice. See, it moves close for increasing u when a is held constant. Obviously, then in that case the stream has the dominance, so the point moves towards the origin, of course. So this statement is again a correct statement, so it cannot be chosen. It is located along the x-axis, of course, too. Okay, so this can also be not a choice. So option B is the only correct option in this case. Okay, like you can see, as U increases with fixed A, stagnation point moves close to origin. Moves close to origin. Okay, is this question clear to all of you? Yes or no? This analysis can be done very easily actually. Okay, like it looks little ambiguous, but in fact this is very simple analysis which many of the students who attended these classes, they know this. Like it's just the calculation of the limit and all normal limits. Okay, so let's see, let's go to the next question then. Are you all okay with this? Yeah, so let's move to the next question. So let's see, in a 2D potential flow, the doublet is a limit of superposition. So when do you get a doublet actually? So doublet is, maybe I'll give you the list of superpositions like this list. Okay, so wherever we see doublet is basically source plus sink placed very close, but yeah, let's see, let me write some superpositions here, superpositions, so that you'll have some idea in case if you don't get time to go through that videos, still it would be very helpful. YouTube hai kya? Yeah, it is on YouTube. Okay, so that's what I'm telling. We have generated a playlist, okay, for recently, like let me tell you the exact name of the playlist. So if you open this Gate Wallah mechanical channel, then you have this playlist called you can see a Gate 𝐂𝐸 𝐬𝐸 with special topics, correct? So you can see there are 12 videos in that Maha Abhyas playlist. So you can open that. Out of the 12, 5 videos are these potential flow videos, okay, where you have some good understanding of the topics. Okay, so let me open back the chart. About, okay, all of you are able to see the playlist, I think. Gate 𝐂𝐸 𝐬𝐸 with special topics, that's the name of the playlist. There are 12 videos in that, so please go through them. Okay, you'll understand all these potential flows. It's very simple. In fact, those lectures you can listen at 2x also. It's very simple stuff. Okay, so first, uniform flow plus source gives you a Rankine half body. A flow past, this can be simulated as flow past a Rankine half body. Then source plus sink of equal strengths placed close. This gives you a doublet. Okay, then uniform flow plus doublet, this gives you flow past a stationary cylinder. Flow past a stationary cylinder. Okay, then if you want to rotate this cylinder, you should give a vertex. So this gives you uniform flow plus doublet plus vertex. So this gives you flow past a rotating cylinder. Flow past a rotating cylinder. Okay, so there is also one more thing which is called Rankine oval. Maybe you can see. So uniform flow plus source plus sink. So this gives you a Rankine oval. Okay, so this is the superposition. You may ask me what is the difference between this and this. In a doublet, the source and sink should be of equal strength and they are placed close to each other. Okay, so here in case of a Rankine oval, even though the source and sink are maybe of same strength, but you will put them a bit far. Okay, it's not very close. So in such case, you will see that it will form a Rankine oval. Means basically you can see there is a oval which gets formed and the flow happens in this direction. Like for example, let's say this is sink and source and the flow is coming in this directions. Okay, so that's how you get a Rankine oval. So but anyway, in this case the doublet is the limit of superposition of this. Okay, a source and sink of equal strength. So that's the limit. Basically, it's a limit. So we place them very, very close to each other. Okay, that's what we get. Okay, so these are the superpositions which normally can have the complex potential functions for each of these flows. It's very easy. Okay, see, doing this in complex numbers is pretty easy. All you have to do is just multiplying two complex numbers, adding two complex numbers. That's all. Nothing other than that. Okay, as far as the math part is concerned. And fluid point of view, you have a lot of significances and deductions from the from these problems. Okay, so let's see then. Okay, I hope it's clear to all of you. So let's move to this question. In a potential flow, a uniform stream of strength U directed along the x-axis and 4 line sources of strengths pi by 2, minus pi by 3, pi by 4, minus pi by 4. When strength is negative, it is a sink, so it captures the liquid. Okay, placed along the x-axis at x is equal to 0, 1, 2 and 3 respectively. The strengths of an additional line source to be placed at x is equal to 4 such that a closed streamline encircles all 5 sources is dash. So let's see. You have an x-axis. Anyone with the answer, you can type meanwhile. So you have an x-axis and let's say this is y-axis. Then there is a uniform stream directed along the x-axis. Okay, so let's say there is a uniform stream which is coming up. So it's coming at with velocity u. Now there are line sources of strength pi by 2 at origin. Then at x is equal to 1, you have minus pi by 3. So at this point you have 5 by 4, and at this point minus pi by 5, and you have some source of strength q, let's say. Okay, so some source is what you have it. So let's say, let's call this source to be m, for example. M is the strength of the source which you have put at that 5th location. Okay, so now this is x is equal to 0, 1, 2, 3, 4. X is equal to 4 actually. The strength of an additional source to be put at x equal to 4 such that a closed streamline encircles all the 5 sources. So basically you could see there should be a closed streamline which should enclose all the cycles. Okay, sorry, all the sources. Means if you take some liquid in this, then the liquid in the streamline stays in the streamline because flow cannot occur across the streamline. So whatever is the flow inside, that stays inside. Okay, so for normally in reality we have, if there are n number of sources and the radius of this source from the origin is ri, for example, okay, and this is mi, then for the streamline to be closed, for the streamline to be closed, summation of all the sources into ri is equal to 0. So basically when you do the superposition, you will figure out one thing, that the moment of each of the source about that origin should be 0 actually. Okay, so that's how you can get it. So first source, what is the first source? Pi by 2 into 0 plus minus pi by 3 into 1 plus pi by 4 into, this is at radius location of 2, plus minus pi by 5 into this radius of location is 3, plus m into, you don't know this m, and this into radial location is 4 is equal to 0. Okay, so normally I'm just giving you the idea, I'm not deriving it as of now, but you can see when you have the sources at different locations, let's say normally these are along x-axis, but in general sources can be at any location. Okay, so if all those sources has to be enclosed by a streamline, then the summation of moments of all the sources about the origin should be 0 actually. Okay, it's a very powerful condition in potential flows. And so if you simplify this, then let's see what do you get. You can have this term is 0 anyway, so 4m or m is equal to 1 by 4 times of pi by 3 plus 3 pi by 5 minus pi by 2. That's all. Okay, so this gives you the answer. It should be 3 pi by 20. Okay, what is the value of 3 pi by 20? Let's calculate. So anyway, we have the calculator, so let us do straightforward. Pi by 3, yeah, correct. So pi by 3, okay, so this is pi by 3 plus 3 pi by 5 plus 3 pi by 5, okay, so this is plus 3 by 5 minus pi by 2 minus pi by 2. So 1.36 divided by 4, 0.34 is what you're getting, correct? So m is equal to 0.34. Yeah, so 0.34, right? We did not do any mess, correct? You're getting 0.34. What are the units, corresponding units? So this should be the strength of the source that you should have. Okay, the summation of the moments of the sources should be 0. So pi by 2 into 0, because that's at origin, minus pi by 3 into 1 plus pi by 4 into 2 plus minus pi by 5 into 3 plus m into 4 is equal to 0. So m is equal to 1 by 4 times of pi by 3 plus 3 pi by 5 minus pi by 2. So I think 0.34 is the correct answer. Okay, are you all getting this? If you do this equation, summation of q into in fact there are many aerodynamics books which use q, so that's why I'm saying q many times. So but in reality you can say sigma mi ri should be 0. Okay, so type in the chat box, is this clear to all? Okay, so 0.34 is what you're getting. Okay, in fact the sources need not be on the x-axis, they can be at any points. Okay, so this r actually means the radial location of the source from the origin. Okay, that's the case. So let's see, consider a 2D potential flow over a cylinder. If the free stream speed is u infinity, maximum speed on the cylinder surface is dash. Anyone? So what is the what do you mean by the maximum speed? See, I'll tell you this story of rotating cylinder in a small brief actually. So if you have a cylinder, okay, and let's say if this cylinder is rotating, for example, say anti-clockwise at some angular velocity omega. Okay, so this cylinder and length of the cylinder is perpendicular to the board. Okay, and then it is evolving. So when this is rotating at an angular speed of omega, if you see, you have maybe at this I have done too steep, let me erase this. So if you see, it has two stagnation points in reality like this. Okay, so it has, I'm very bad at drawing these free curves. Okay, maybe I'll show you, because if I keep drawing this will take ages. See, okay, so if you have the rotating cylinder, this is the analysis for the rotating cylinder actually. So if you look at the streamlines, so this is how you get the streamlines. Okay, so basically on the bottom side you have the same thing, but on the top side you will end up with two stagnation points. Okay, so when you have these two stagnation points, what is the maximum speed? The simple analysis tells you that when you rotate the cylinder faster, this stagnation points keep moving up, means these two stagnation points keep moving along the cylinder surface, and when you use the maximum speed they actually merge. Means what is the meaning of maximum speed? You see, this sin theta becomes 1 in that case. Okay, so theta becomes merged. So you can see there are two angles for theta, but at when you write it, when you do at theta is equal to 90 at the maximum speed, you will have a single stagnation point. Okay, so this condition is what we have seen. Anyway, let me use my skills. Normally these have to be plotted in MATLAB, okay, so that you would get some nice idea. Normally I plot these things in MATLAB in general, but anyway, so let's see, you'll have two stagnation points, okay, such that one is at a triangle theta s, and this is 180 minus theta s, obviously. Fine, so this is 180 minus theta s. So if you see, this sin theta s is given by circulation by 4 pi u, where u is the free stream velocity which is coming onto the cylinder, into radius r of the cylinder. So if you have the radius of the cylinder is r, so this is what you would get. Okay, and so then if you see, we have two angles where when sin theta s is equal to 1, this implies theta s is equal to 90. This corresponds to maximum speed, where these two stagnation points, like you can see when theta s is increasing, this point keeps moving up, this point also keeps moving up, and at theta is equal to 90 they actually merge. Okay, so then this gives you circulation should be equal to 4 pi u r. Like the same analysis, even you can see I have shown here, like for example you see the sin theta value is equal to circulation by 4 pi u infinity. Maybe I have taken the radius as a, that's all. Okay, but a is nothing but the radius of the cylinder, so I have taken r in this analysis. So this circulation is nothing but u theta into 2 pi r. You can derive this again, it's a very small thing, you know, circulation is nothing but cyclic integral over the path v dot dl. Okay, so if you do this line integration, you'll end up with circulation is equal to u theta into 2 pi r is equal to 4 pi u r. So this becomes 2, radius gets cancelled, so u theta is equal to 2 times the free stream velocity. So this is the condition. So the peripheral velocity on the disk should be, on the cylinder should be twice the free stream velocity of the flow. Clear? So that's how you have u theta is equal to 2 times of u infinity, which is here. Okay, this all notes whatever I am teaching you, you can find in the videos. So if you want better clarity, you can go to the videos. Okay, so C should be the correct answer. That's when both the stagnation points merge and you'll see a single stagnation point in case of a rotating cylinder. Okay, yeah, type it in the chat box. Is this okay to all? Every one of you. Okay, yes. So now let's go to the next question. So let's see, it's a CART question, basically fixed support, a large water tank based on RTT. Okay, linear momentum equation. Yeah, maths is complete in that. Okay, you can have sequence and series, you can have Cauchy's test, integral test, anyway, all these things, and you also have this differential equation, power series solutions, all this stuff. Okay, you can see it has complete syllabus. Okay, in the Maha Abhyas part. So let's see, a large water tank is fixed on a cart. So there is a cart here, you can see there on this cart there is a water tank which is sitting and a vane. So there is a vane like this. The wheels on the cart provide negligible resistance. So here at this locations of the wheel, the friction is very small. For rolling on the fixed support, the cart is tied to the fixed support. So the cart is tied to the fixed support with a thin horizontal rope. There is a hole of diameter 5 centimeters on the side of the tank. So there is a hole of 5 centimeter diameter on the tank actually. Okay, through which a jet of constant velocity of 10 meters per second emerges. So this jet has a constant velocity of 10 meters per second. The jet of the water is deflected by the vane attached by 60 degrees. Okay, attached vane by 60 degrees. So see figure. Okay, I have seen figure. So this is the 60 degrees jet deflection by this vane actually. Okay, assume the jet velocity remains constant at 10 meters per second after emerging from the vane. So here the velocity is 10 meters per second after emerging. Take density of water to be 1000. The tension in the connecting rope. So obviously first let's look at the physics. Why this rope is under tension? Because when the fluid is coming in this direction, this tank will try to move forward because of the reaction force, correct? So we are not facilitating the movement of the cart, and we have tied this to this fixed support, and there is a string which is connecting, or rope, whatever. So when this cart is trying to move in this direction but it is tied, then the rope becomes tight and there is a tension in the rope actually. So our job is to calculate what is the tension. Is this okay? Question clear to all of you? Everyone, please type in the chat box. 98.2 newtons, 2 newtons, maybe, I don't know. Let's solve. Okay, fine. So let us solve. First, did you all understand the physics? We'll see the maths involved. Okay, yes. Now let's see, let us take a control volume. So since we are analyzing the tank, let us take this tank plus cart, whatever is the control volume actually here. Okay, so this is my control volume. So this is control volume. Control volume. Okay, so solve similar problem. Okay, good. So let's see in this case. So if you draw the control volume, definitely there is this tension in the rope which is acting, correct? So this is, there is some tension T. So let us apply the RTT, Reynolds transport there. So by RTT, sigma Fx on cut is nothing but sigma Fx on cut by fluid plus sigma Fx external. Okay, so sigma Fx external, clear? So this is sigma Fx external. Now if you take this cut, on this cut there is only one external force which is T. So let's define the coordinate system x and y axis, for example. Okay, so you have x and also you have y, of course. So then in this case, sigma Fx external, this external we have only tension T. So this is tension T which is pulling the cut up. Now what is sigma Fx on the cut by the fluid? So this is nothing but sigma m dot v x at the inlet minus summation m dot v x at the outlet plus T. Okay, so this is what you have, because from RTT, you know, force acted on the control volume by the fluid is nothing but rate of change of this momentum in the x direction of the fluid, in minus outlets. Okay, because it's on the cart. Now the cart is in static condition, so because of all these effects whatever are there, the cart is in static condition. So if the cart is in static condition, this sigma Fx on the cart is 0, correct? Yes or no? Because the cart is not moving, so it has some static condition, so definitely the sigma Fx acting on the cart is 0, because if there is some force the cart would have moved. Yes, so if you simplify, first of all, if you take the control volume, this control volume, okay, so you have this control volume. Actually in this control volume, is there any point on the control surface where fluid is coming inside the control volume? Sorry, so can someone identify any point on the control surface such that to that point on the surface the fluid is coming inside? Anyone? No, obviously, correct? So there is no momentum which is entering the control volume. So definitely this term is 0 because there is no inlet onto the control volume. Okay, so this implies 0. So if you simplify this, we have, if you equate this to 0, the tension T in the rope is nothing but summation m dot Vx in the outward. So what is the mass flow which is coming out? So let's see, here you have some area of cross section, let's call it A. Of course we know D naught, so we'll calculate the mass flow rate, and let's call this as V, for example. Okay, and this V has 60 degrees, so clearly this is V cos 60 and this is V sin 60. Okay, so the x component of velocity at this location is V cos 60, correct? So m dot into V cos 60 is what you have actually. Okay, and rho av square cos theta, maybe, let's see, and m dot, you can write m dot as rho av, so rho area v square into cos 60 is what you have, and cos 60 is 1 by 2, so rho a v square upon 2. So that's the tension in the rope actually here. Okay, so therefore T is equal to rho a v square upon 2, and if you simplify this, density of the water is 10 cube, then area of cross section of the flow, this is a outlet of 5 centimeter, so pi by 4, 5 centimeter, so 0.05 meters, so square into velocity square, so velocity square is 10 square divided by 2 actually. Okay, so if you simplify this, you would get the answer in newtons. And what are the units they are asking you? They are asking you in newtons, round off to 1 decimal place. Good. So let's see, this can be written as 25 into 10 power minus 4, so this is 5 actually, so 125 pi by 4, let's see, 125 pi by 4, 98.17, yeah, 98.17, so this goes to 98.2 newtons. Okay, so this goes to 98.2 newtons. Clear? If there is no rope, then cart moves with a constant velocity or there is some acceleration. Initially during the jerk period there is some acceleration, but once it comes to steady state it moves with uniform velocity. Okay, because in reality what happens is, this is an ideal case, so you experience cart is accelerating, but in reality the speed gets adjusted such that the friction and the propulsion force becomes equal. Okay. Okay, Ashutosh, Ishan, Anurag, Ujjwal, Mahavir, Ufan. I can read these names. So this, did you all understand this question? It's a simple question, but you have to use your concepts little carefully, using the plus minus signs here and there. That's all. Okay. So let's go to next question. So let's see, a square plate is suspended vertically from one of its edges. Okay, so it is suspended from its edges, uses a hinge support as shown. So there is a hinge support. A water jet of 20 mm diameter having a velocity of 10 meters per second strikes the plate at its midpoint. So this is midpoint actually. Okay, so if this is 200, then this height is 100 at an angle of 30 degrees. So this angle between the plate and the jet is 30, or 30 with the vertical, whatever. Consider G as 9.81. Neglect self weight of the plate. The force F required to keep the plate in its vertical position. So one thing is very clear, physics, when you hit a jet, ultimately because of this impact, the plate will try to rotate about this hinge. Okay, but by applying a counter force F, you are keeping it vertically. Okay, so then they're asking you what is this force F that you should need. Okay, so let's see, it's a hinge. Let's draw the free body diagram when you hit it. I'll draw a bit bigger so that you will understand. So there is a hinge here. So ultimately you have the reaction forces Rx and Ry. Okay, so there is a hinge reactions. And what is this hinge? Point is given, nothing is given. So let's call it A. Okay, now because of the impact of the jet at its midpoint, so let's say somewhere here it is the midpoint. So there is some force which is exerted by the jet. So let's call it Fj at some angle 30 degrees. Okay, so now what we can do is we will resolve this force. Okay, so if you do this, we can resolve this force as Fx Fy. Correct? This is what you can resolve, obviously, because there is a force due to jet. So maybe you can write Fjx, force due to jet in the x direction, and force due to jet in the y direction. Okay, this is what you can do. And obviously you have the force F which you are applying here to counterbalance the rotation. Okay, so let's call this point A, maybe this point you call G, and this point maybe some B. Okay, because it's the centroid, that's all. Okay, or center of mass, whatever. So then under this effect of these forces, okay, so you can see under this effect of Fjx, Fjy, F, and this A, your beam or whatever the bar has to be remaining vertical. Okay, so if the bar has to remain vertical under the influence of these forces, for the, you know, what is this called, square plate. Okay, for the plate to be vertical, summation of moments about point A, maybe you take the counterclock sense as positive, so this has to be 0. Correct? So the moments about that point A has to be 0, of course. Okay, then you also know that this angle is theta. Let's call it to be theta, for example, for some time. So if this angle is theta, then clearly this angle is theta. So this is F cos theta, and this is Fj sin theta, because theta I'm calling the angle with the vertical. Okay, so this vertical one would be Fj cos theta, and that would be Fj sin theta. Fj is the force due to jet. Okay, so let's see, if you write the moments, this Rx, Ry, and F cos theta pass through the moment center. Okay, so they do not contribute for any moments of this rotation, but Fjx minus Fjx, because you have the clockwise, Fjx, no sorry, Fjx is anti-clockwise. Okay, Fjx is anti-clockwise, so Fjx, which is Fj sin theta, into, since this is the midpoint, you call this as L by 2, and this part is another L by 2, length of the beam, let's call it L total, so L by 2. Then you have this force F having a clockwise moment about the moment center, so minus F times of L is equal to 0. Is this okay to all of you? See, we are solving fluid mechanics. Okay, so we'll use all concepts of mechanics, but to get some terms in the equilibrium equations, we need knowledge of fluids. Okay, so how fluid mechanics does the job. Is this okay to all of you? By looking at this figure, can you all, because the weight of the beam is neglected, even though if there is weight, then the W would pass through the moment center. Okay, it's clear. Then, so let's see what all you can cancel. This L and L gets cancelled. So F is equal to Fj into sine theta upon 2. So theta is some 30 degrees whatever. Now coming to the force exerted. So what is Fj? That's a question. Okay. So Fj is nothing but force exerted by jet on control volume. Okay. So force exerted by the jet on control volume. Let us do something here. Instead of calculating Fj, let's do something. Let us calculate directly Fjx divided by 2. Okay. So half of Fjx. Let us write it this way, because half of the Fjx is what you will get, and Fj sin theta is nothing but Fjx. Okay. So now let us calculate this Fjx directly. Force exerted by jet on control volume in x direction. In x direction. So let's say this is the x direction and this is y direction. So Fjx on plate by fluid is equal to summation m dot Vx at inlet minus summation m dot Vx at the outlet. Now tell me, if you take this as the point of impact, like for example if you take this as the control volume, because this is the zone in which the momentum of the fluid is changing. So if you take this, the speed at which it's entering the control volume is some velocity v like this. Okay. So if you have this v, okay, so let's write v for the time being. This angle is theta with the vertical. So you have v cos theta and v sin theta, correct? So at the inlet, the horizontal component of velocity of this is v sin theta. Okay. So this Vx is going to be v sin theta. Now at outlet means basically if you see the fluid is hitting and then it's falling like this, then at that outlet, do you have any x component of velocity? Type it in the chat box. Do you have any y component of velocity? Sorry, x component of velocity at the outlet? Do you have any x component of velocity at the outlet? No, right? So you don't have any x component of velocity. Clearly this Vx at the outlet becomes 0, of course. Okay. So m dot rho av, so F is equal to rho a v square sin theta upon 2 actually. Okay. So rho a v square sin theta upon 2. So that gives you this F actually. Okay. So this is v sin theta, m dot is rho av, the velocity which is coming. So rho a v square sin theta by 2, of course. So if you simplify this, then density, it's water jet, so density is 1000. Area of cross section of the jet, it is 20 mm circular jet, so pi by 4 into 20 mm, so 2 centimeters into v square. So what is the velocity at which it's coming? So velocity is not given. Okay, velocity of 10 meters per second. Okay, so it's coming at a velocity of 10 meters per second. So 10 square into the angle is 30, so sin 30 is half divided by 2. Okay, so you should have a 2 here again. That's all. So this is the answer, and this answer is going to be in newtons. So what are the answer they are expecting expressed in newtons? Okay, good. So let's then simplify this. So obviously again 10 power minus 4 and 4. So this 4, 10 power minus 4. So you have a 10 here. Then 4 will cancel this 2.5 times. So 2.5 times pi, that's all. So 2.5 times pi, 7.85. 85 newtons. Yeah, 7.85 newtons is what you're getting. Okay, you should be careful with the 10 powers, otherwise things go strange. Okay, just let me, I think some pop-up is blocking this. Why this pop-up comes every time? Every now and then it comes. Okay, I think it's not going, but is this class okay, going fine to all of you, right? Because I feel like some pop-up is coming and going about the OBS. Okay, but all of you are able to listen the class, right? It's going good. So for irrotational, should be conservative or need not? Which should be conservative? Irrotational flow field is conservative field, no? Yeah, irrotational flow field is a conservative field. Okay. Fine. So 7.85 is the correct answer for this. 7.85 is what you have got. Okay. Then let's solve this question. Water flows in a pipe so that its velocity tipples every 20 seconds. At time t equal to 0, as t is equal to at t equal to 0, it has u is equal to 5 meters per second and v is equal to, so this is v vector is equal to u of t I cap, where u of t is given by this function, time function. Okay, so obviously if you put t equal to 0, it is 3 power 0 1. After 20 seconds, this 3 power 20 becomes 3 power 1. Similarly, after 40 seconds, 3 square. So after 60 seconds, 3 cube. So after every 20 seconds, its velocity tipples. That's what it's even given. Its velocity tipples every 20 seconds. If t is equal to 20 seconds, then the acceleration is dashed I cap meter per second square, round off to 3 decimal places. So let's see. We have a very simple question. Given v is equal to 5 times 3 power t by 20 I cap meters per second. Okay, so at t equal to 20, what is the acceleration? That's what ATT weightage in XCE, around 6 marks, 6 to 7 marks. Okay, oh sorry, you're asking about the marks, no? Yeah, around 10 marks. Okay, 8 to 10 marks it can come up. Okay, normally for some 4 or 5 questions come up, so let's say 3 1 mark and 2 marks, that can contribute around 8 marks. Okay, sorry, 7 marks, 7 to, okay, 7 to 9 I think. Yeah, 7 to 9 marks you can get, but that's still big out of 35. So 11.25 anyway. Let's see. So if you look at acceleration, dou v upon dou t plus v dot del operating on v, but since it has only t, then definitely this term is 0. Okay, this term is 0 because it don't have any involvement of space coordinates. It's changing only with time. So if you differentiate this, dou v by dou t, so 5 into, if you differentiate this function 3 power t by 20, it's like a power x, so a power x into ln 3 into 1 by 20 times I cap, that's all. Okay, so because you see integration, or since d by dx of a power x, this is nothing but a power x into ln a, but this function x should have another derivative which is like 1 by 20 in this case, I cap. So at t equal to 20 seconds, at t equal to 20 seconds, a bar is going to be 5 times 3 power 20 by 20 into ln 3 into 1 by 20 I cap. Okay, so this is 3 and this is 4, so this gives you 0.75 into 0.75 into ln 3 I cap. Okay, so what is this value? 0.75 into ln 3, 0.75 into ln 3, 0.8239. You are getting 0.82. Yeah, 0.8239, so 0.824 I cap meter square per second. Sorry, this is not kinematic viscosity, meter per second square. 0.82, yeah, so 0.8239, so you can round off to 0.824. Okay, MTech in Industrial Engineering, which institute should I prefer? IIT Delhi if industrial, or IIT Bombay? You can go to any of these 2 places. In fact, 𝐂𝐚𝐴 is also doing very good. So 𝐂𝐚𝐴, IIT Bombay, Delhi, one of these 3 places. Okay, ripples every 20 seconds. See, What do you mean by tuples every 20 seconds? At time t, if you write velocity, magnitude of velocity, for example, when time t equal to 0, you put t equal to 0, this is 3 power 0, 1, so you have 5 as the velocity, okay? So after 20 seconds, at time t equal to 20 seconds, if you put t equal to 20, you have 3 power 1, so 5 3s are 15. So at t equal to 20 seconds, the velocity is 15, okay? So within 20 seconds, its velocity is tripled, okay? 5 into 3 is 15. So again, after next 20 seconds, means by the time you reach 40 seconds, if you put t is equal to 40, this is 3 square, 5 9s are 45. So again, it got 3 times, okay? So this is how the velocity profile is given, that's all. Doesn't matter much, okay? That's what they mean, like velocity triples every 20 seconds, okay? And this is a differentiation of exponential function where base is constant but exponent is a variable, okay? Yeah. IITM, but what are the institutes we have discussed? So that's better than IITM as far as industrial is considered, at least, okay? Hi Vijay. So IITM, KGP, IME, okay, I think it's good. You can do a better bit of more research, okay? Because like you can see, after the completion of the GATE exam, we have a lot of these sessions which could talk about each program at each institute, okay? So after listening to all these programs, you can decide, because COEP opens only after the scorecard comes out, okay? But these sessions of post GATE guidance start immediately after the GATE exam, so you can decide at that point, okay? Are you giving XE this year? Okay. Third ampere decision still. Got it, sir. Thank you. IITM. ISC don't have industrial in particular, but few people in math, they do the operations research and research based activities, but not for dedicatedly industrial engineering, okay? Yeah. Fine. Whether I'll know whether I'll write GATE exam or not, that's a decision that we make on the morning of that exam day, okay? Hello, let's see. So this is 0.824, okay? Many guys get issue with this differentiation, so please do this differentiation carefully. This is what you have, okay? Or you can see, maybe in fact if you generalize this, I'll write this a power f of x. If you have some function where a is a constant, then a power f of x ln a into f dash of x. That's all, okay? So let's solve one more question. The velocity components of a particle in the flow field are defined by u is equal to 3 meters per second and v is equal to 60, where t is in seconds. If the particle is released from the origin at t equal to 0 seconds, the path line equation is given by x square is equal to ky. So the value of k, round off to the nearest integer, okay? So let's see. The velocity components of a particle in the flow field. So if you have this v, this is 3I plus 60j, okay? So which is like x component is 3. That's what of course they have given. Yeah, v is equal to 60 meters per second, right? So v is changing with time, where t is in seconds. If the particle is released from the origin at time t equal to 0, so at time t equal to 0, the particle is at origin and then it is released, okay? So then the particle moves. Fine. After so everything depends on third ampere. No, no man, you cannot take things for granted, okay? So let's see. U is equal to 3. So what is u? So I have told you, normally people have this misconception in the mind, like dx by u is equal to dy by v. This acts as path line always. No, okay? This is valid only if the flow is steady flow, okay? So if there is no involvement of time, then since streamline, path line, streak line, all these lines becomes identical. So that's why the equation of the streamline also satisfies the path line equation, okay? But in questions like this, where there is involvement of time t in the velocity profiles, you won't have a this equation will not be valid. I'll show you why, okay? First let us do the actual path line equation, then I'll show you using this equation what issue you will face, okay? So let's see. U is nothing but dx by dt is equal to 3. So dx is equal to 3 dt. So let us integrate this, okay? For integrating, you can integrate x equal to 3t plus constant, then substitute boundary condition. Rather than doing all this stuff, you can do something. At time t equal to 0, the particle is at origin, so x is also 0. So at some time t, you don't know what is the location x. So if you solve these definite integrals, x is equal to 3t is what you would get, okay? So x is equal to 3t. Similarly, if you take y, So dy by dt is equal to 6t. So dy is equal to 6t dt. You integrate this guy again from t is equal to 0. At t equal to 0, this y coordinate is also 0. You see it's at origin. So at some time t, this is at some y location, which you don't know right now. So y is equal to, so integration of 6t is 3t square. So this is what you should get. Y is equal to 3t square. So now from these two, at the same time instant, if you want to connect x and y, so at a given time, what is the value of x and what is the value of, sorry, something, what is 3? K value is 3. Okay, maybe. Let's see. So you call this equation 1. You call this equation 2. Okay. So from 1 and 2, this implies y is equal to 3 into this t can be written as x by 3 whole square. So this equation is x square is equal to 3 times of y. It's a parabola basically. Okay. So the path of the particle is parabolic. Clear? So k should be 3. Yeah. So this is the way to solve the path equation. Okay. So if you have u, then you equate dx by dt and simplify. Okay. If there is involvement of y, for example, in this velocity profile, you can take y as constant because you have a derivative with respect to space. So with respect to x direction actually. So you can treat other space variables like y, z, these things constants for getting this solution. So this gives you some function of x by t equal to 0. This also gives you some function of x by t equal to 0. From both you eliminate t, you will get the path function. Okay. Now if you apply dx by u equal to dy by v. What is the mistake? I'll tell you. Look, if you write dx by u is equal to dy by v, you have involvement of time here, but do you have any derivative with time? You have involvement of time, but do you have any derivative of with respect to time? No. So you cannot integrate this obviously. Okay. So that's the mistake. Generally this equation is valid only when there is steady flow. Then in case of steady flow there is no time and you have xy, you can integrate and get the things easy. Okay. So dx by u equal to dy by v is path line only if the flow is steady. Otherwise this is the common way to work out. Okay. So let's solve this question. It's a nice question again. Oil flows between two parallel plates, one of which is at rest and other moves with a velocity of u. What is this flow called? Where you fix one plate and the other plate moves. What is this flow where you fix one plate and other plate moves actually? Quiet flow. Correct? It's basically the quiet flow. So you have this quiet flow. Then, so let's say you are fixing the bottom plate, for example. You are fixing this bottom plate and you are moving the top plate. Okay. You are moving the top plate. So let's say you are moving it in this direction with a velocity u, and this is fixed. Okay. So then, okay, anyway, it's fixed. So this is y horizon and x axis. Let's say this is x axis. Okay. Yeah, it's quiet flow. Then if the pressure is decreasing in the flow direction, so in this direction pressure is decreasing, so it's a favorable pressure gradient at a rate of 5 pascals per minute. So if you take this as the x direction, given dp by dx is equal to minus 5 pascals per meter. Why I put a minus? Because it is decreasing actually. Okay. So when you increase the x, this p drops. So there is a minus 5 pascals per minute. Dynamic viscosity mu is 0.05 kgs per meter second. The spacing of the horizontal plates is 0.04 meters. So you call this, for example, some distance h. So you have h is equal to 0.04 meters. So it's like 4 centimeter small gap. And the volumetric flow q per unit width is equal to 0.02 meter cube per second per meter. or meter square per second if you simplify directly. Okay, meter square per second, or this is meter. Then the velocity is dash meters per second. So velocity of the plate which is moving. Okay, so what is this? U, of course. So what is this velocity? U. Clear? So let's see. They have given the discharge. So by chance, do any one of you remember the expression for the discharge actually? Any one of you, did you remember the expression for the discharge? So if you see, Q is equal to U infinity into H into width of the plate times the non-dimensional term 1/2 plus alpha by 6. Correct? This is the expression for the discharge in case of a coed flow. 2. If you take any cross section, then the flow which is across this cross section is given by this result, and of course in this case this width value, width of the plate is 1 unit. That's all. Okay. And what about alpha? Alpha is called non-dimensional pressure gradient. Non-dimensional pressure gradient, and alpha is h square by 2 mu u infinity minus dp upon dx. That's what you have, the non-dimensional pressure gradient. Okay, so now you have this Q. U infinity is nothing but the movement of the velocity of the plate. So in this question, this U infinity is given as U. So we have to calculate what is that U actually. Okay, so let's see. So this equation gives you Q is equal to U H times half plus alpha by 6. So alpha by 6 is h square by 6 times 2, 12 mu u infinity, which is U, into minus dp by dx. Okay, so this equation is a quadratic equation, or you can also solve. So can you solve it from Navier-Stokes equation? You want me to solve right now? It's a derivation, like it takes 5-10 minutes, but if some of you want me to solve, I'll solve, no issue. It's a simple case. You just have to plug in some boundary conditions. We'll solve this. How this? Or shall I show you in my notes, or else? Okay, fine. I'll solve, no issue. So let's first finish this problem, accept this formula, then I'll solve. Okay, using the Navier-Stokes equations. Okay, basic idea you want. Okay, I'll give you. First, let us solve this question. So if you simplify this, it can be quadratic equation in U, but if you solve, let's see, Q is equal to U H by 2 plus U H cube. So then this U and U gets cancelled. So H cube by 12 mu into minus dp by dx. So you want this U actually. So U is equal to 2 by H times Q minus H cube by 12 mu into minus dp by dx. That's all. So this is the free stream velocity of the plate, or the velocity at which the plate actually moves up. Okay, so let's see. So you have the values, no? Let's put it. 2 by, what is this H? 4 centimeters. Q. So what is the discharge? Discharge is 0.02 minus H cube by 12 into mu. So what would be mu? Dynamic viscosity is 0.05 kg per meter second. So we have seen kg per meter second or Pascal second, the conversion factor is 1. Okay, you need, if something is given in kg per meter second, then you want it in Pascal second, you need not change it. Okay, the value remains the same. So 0.0, how much it is? Sorry, 0.05. Okay, 0.05 into the pressure gradient minus dp by dx. So minus of dp by dx is 5. That's all. Okay, you should not again put minus 5. Okay, so this is already minus of dp by dx. So dp by dx is minus 5. So minus dp by dx is plus 5 actually. So this value would be in meters per second. What are the question units they want in meters per second, round off to 2 decimal places. Or else you can solve this using quadratic equation also, doesn't matter, but it's a simple way to do. So let's take the calculator. 0.04 cube by 12 into 0.05 into 5. So subtract this from 0.02. So subtract this from 0.02 into 2 by 0.04, 0.973. meters per second. Okay, so this is 0.973, 2 decimals, so 0.97 meters per second. Okay, did you all get this 0.97? Okay, when answer comes 0 point something, I doubt of some mistake in calculation. Why? You can have the answer no with 0 point something. So since some of our friend is asking, just let us give some basic brief idea. So if you look at 𝐂𝐻 flow, I won't dive fully, but I'll just give you some idea. Okay, so if you take this, let's say nothing is changing in the z direction. So let's say width of the plates is so big, so you don't see any significant change. So dou by dou z of anything with respect to z is 0, and things are changing only in the x and y directions. Okay, now if you start with the Navier-Stokes equation, the general Navier-Stokes equation, rho times body force minus gradient of P plus mu times del square V actually plus mu plus second coefficient of viscosity gradient of divergence of V is equal to rho times acceleration dV by dt. So this is what you have the generalized Navier-Stokes equation, correct? Normally for any flow with Stokes approximations, of course. Okay, so this is the Navier-Stokes equation. Lambda is the second coefficient of viscosity, and normally this lambda you will see. Okay, so lambda is minus 2 mu by 3, but of course not very much valid in the compressible flow regime, so we'll keep it as lambda. Okay, then first if you look at the flow to be incompressible, okay, if there are no compressibility effects in the picture, then this divergence of V is 0, so this complete term blows to 0. Okay, then normally if you take this as flat, like there is no inclinations or something, so that gravity is acting. So let's say the body force acting on this is 0. Okay, there is no gravity driven flow is not there here. Okay, there is nothing which is driven by gravity or any body force. Like normally you can have, apart from gravity, you can have electric fields, magnetic fields, things like this, but nothing of such sort is there. So gradient plus this dynamic viscosity values and rho times dV by dt actually. Okay, so let us look at each of these terms, of course. So mu into del square V, so V is equal to, firstly if you take a particle here, the spacing is so small, y is equal to 0 and y is equal to h actually. Okay, so then if this spacing is very small, the bulk motion of the flow can be only along x direction, correct? Because the fluid cannot flow in the y direction bulkily, because the plate boundaries will come, and W width of the plates are so large, so nothing is happening effectively in z direction. Okay, so which means this V has only velocity along x direction. There is nothing, no story about the y directions. Okay, so if you see only U, if you look at this component and things are steady, okay, it is already steady, fully developed, all this case is there, so it is steady actually. So then if you calculate dV by dt, dou V by dou t plus V dot del operating on V is what you have. Okay, and since you have taken steady, this is 0. Now obviously you have flow only in the one single direction. This term is nothing but dou U upon dou x, that's all. Okay, so U into dou U upon dou x. V is 0, W is 0, so rest all terms are 0. So the acceleration is only this, but this dou U by dou x is actually 0 because the flow is fully developed. And also you can see this from continuity, like since you have taken incompressible in 2D is equal to 0, so first of all this V is 0, so which gives you dou U by dou x is equal to 0 from continuity. Okay, so which tells you when you move between this point and this point, you cannot find any variation. That's what, understood? For a given steady operation of the flow, then you can't find any difference in velocities between this point and this point. So when x is changing, you can't find any difference. That's what this equation tell you, and that's what even the fully developed conditions tell in reality. Okay, so this is 0. So whatever the accelerations you have, this term is also 0. Now there is a balance between pressure and inertia. I mean the pressure and viscous forces. Okay, so if you see in 1D, this equation can be written as minus dou p by dou x is equal to mu times dou square u by dou x square. This is, sorry, dou y square. This is what you have because u is changing with respect to y. So minus dou p by dou x is equal to mu times dou square u by dou y square. So under these assumptions and this understanding, this full equation gets converted to this small equation. Got it? Yeah. Okay. And you will also see the pressure equations, like if you do the momentum balance, if you simplify the momentum equations in the x, y, z directions, these momentum equations simplify that pressure is purely function of x. Normally pressure can be function of both x and y, but in this case you will see when you write the y direction momentum equation, you will see dou p by dou y is equal to 0. So p is only function of x, so this becomes exact derivative. Okay, and u is function of only y, this also becomes exact derivative because dou e by dou x is 0. So if you do these things, minus dp by dx is equal to mu times d square u by dy square. Now you have one logic that one side of this equation is purely function of x. This is extremely function of x because p is only function of x, so you differentiate that with respect to x, you'll again get function of x only. Okay, similarly u is function of only y, so if you differentiate it twice with respect to y, you'll get again y, of course. So equating this function of x with function of y at all the points can happen at only one case, when it is constant. That's how you have a uniform pressure gradient in the flow. And in this question also, whatever you have solved, you'll see dp by dx is equal to 5, which is a fixed constant. Okay, because this has to be constant if this equation has to match. Then you have a differential equation, single order differential equation. You solve it, then you will end up with the velocity profile. U by capital U is equal to y by h plus alpha y by h into 1 minus y by h. This is the velocity profile which you will get if you solve this equation with two boundary conditions. What are the two boundary conditions? At y equal to 0, the layer of the velocity of the layer is also 0 because of no slip. Similarly, at y equal to h, u is equal to capital U. So this is a second order differential equation. To solve this, you need two boundary conditions. One boundary condition is at y equal to 0, u equal to 0. Second boundary condition, at y equal to h, u is equal to capital U. That's all. If you apply, then you will get this velocity profile. Okay, and once you get this velocity profile, then you can calculate whatever you want, discharge, okay, wall shear stress, anything you can do. So I learned the velocity equation as sum of normal 𝐂𝐡 and plane Poiseuille, and then find average velocity and using q equal to av. Is that correct approach? Sorry, I learned the velocity equation as sum of normal 𝐂𝐡 flow and plane Poiseuille, and then find average, because you mean to say that both are fixed, so you take average, but the physics changes actually there. Okay, the equations look very similar, but you know, there in that case the inertia terms will also make impact. Okay, because there is fluid on there is this plate on both the sides, the not inertia, sorry, the viscous terms will greatly affect. Okay, this approach I don't think you'll get the correct answer, because in one case it's like 𝐂𝐡 flow because you are taking 𝐂𝐡 flow and you are calculating discharge. Okay, and that discharge is what it's given in this case. Prashant, Swami, is this okay to all of you? Did you understand how did we achieve this velocity profile from this equation? Yeah, Sharma, I learned the velocity equation as sum of, yeah, that's what I'm telling. That could not give the correct answer, because if you are getting the average velocity of plane Poiseuille flow, then that itself, right? Why to connect it with plane 𝐂𝐡 flow again? See, these flows are independent. Clear? It's not like, since one, in such case, whatever you are telling, out of the complete case only one plate is moving. General velocity equation for this flow, this is the velocity equation, no? General velocity equation. You take any guys, is it okay now? Now okay? Yeah, there was some small issue, I think. There was some. Is it okay now? Please comment in the chat box. Okay, fine, right? Because I think these issues are again and again coming up, but it's okay, right? So let's continue. So I hope this is clear. And this is the velocity profile. Someone has asked me to write the general velocity profile. So this is the general velocity profile. It depends on the value of alpha. Okay, if alpha is 0, like the simple coed flow, basically where the pressure gradient is 0, you have a linear velocity profile. Okay, if alpha is non-zero, then you have parabolic profiles which you generate. Okay, so that's how here the answer is 0.973 actually. So let's go to the next question quickly. So let's see. The envisaged incompressible flow field resulting from a uniform flow past a circular cylinder of radius r centered at origin is given by the coordinates is given by u is given by this, where u and u are, I think. Okay, this is u r and u theta. U r and u theta are the radial and azimuthal directions, azimuthal components in polar coordinates, of course. U is the free stream speed. Ignore the effects of gravity. The azimuthal location in the first quadrant on the cylinder at which the pressure coefficient is 0 is dash degrees. So what should be this answer? Can anyone tell me? Direct, do you remember what I have taught you in class? It's a flow past a stationary cylinder. So in the first quadrant, so basically this angle theta where the pressure coefficient is 0. What is pressure coefficient? Basically Cp is equal to P minus the free stream pressure by half rho u infinity square. 30 degrees, correct? So this should be 30 degrees. Like again, I'll show you some of these notes so that you would get this. So this is rotating cylinder. So let's go for a stationary cylinder case. Okay. So in this stationary cylinder, yeah. So identifying the location of stagnation points, and after that we define something called the coefficient of pressure Cp. Okay, and this Cp value comes out to be 1 minus 4 sine square theta. And if you plot this function, then you will see at pi by 6 you'll have a point where the pressure P is exactly same as the free stream pressure, and the coefficient of pressure at that point is 0, of course. Okay, so let's see. Cp is equal to P minus P infinity by half of V square, and Cp in this flow past a circular cylinder (1 minus 4 sine square theta). Okay, and if Cp is equal to 1 minus 4 sine square theta, so if you equate this to 0, then you will see sine theta is equal to plus or minus half. Okay, so theta can be pi by 6, 7 pi by 6, 5 pi by 6, and 11 pi by 6. So out of these things that lies in the first quadrant, so this value lies in first quadrant. Okay, so pi by 6 is nothing but 30 degrees. Okay, normally you can show this from the Bernoulli equation and all. So here the velocity on the radial component, okay, and the velocity at the free stream. So by comparing these things you can get the answers. Okay, this is what in fact we have done in this class notes. So you can see we have applied the Bernoulli equation on at free stream location, and also this is the free stream location, and this is on the surface of the cylinder. So on the surface of the cylinder you will see the magnitude of velocity on the surface of the cylinder is given by 4 u in square sine square theta, and by using this understanding we'll calculate same thing I have written here. Okay, so theta is pi by 6, 5 pi by 6, 7 pi, and 11 pi by 6, of course. So this is 30 degrees. round off to the nearest integer, no need of round off, it's an exact value, it's 30 degrees on this case. Okay, so next let's look at another case. Question: the magnitude of x component of a unit vector at the point 1 comma 1 that is normal to equipotential line of the potential function phi of r is equal to 1 by r square plus 4, where r is root of x square plus y square is dash. So let's solve this question. The magnitude of x component of a unit vector at the point 1 comma 1 that is normal to the equipotential line of the potential function. So let's see, there is a equipotential line, of course. So this is the equipotential line, so which is 1 by r square plus 4. 1 by r square plus 4. R is root of x square plus y square. Magnitude of x component of a unit vector at the point 1 comma 1. At the point 1 comma 1. So let's call this point as 1 comma 1. So the normal vector. So this normal is given by gradient of phi. Correct? So that normal is given by gradient of phi. X component of unit vector. Okay, so let us do something. If you convert this r square to x square plus y square, because they are asking you in the x component. Okay, so if you look at x component, gradient of phi. Okay, let's do a simple case. This phi of r is function of x comma y. So 1 by r square is x square plus y square plus 4 actually here. Okay, so that's what you got. It's independent of theta maybe, so it's a radial line, of course. So 1 by x square plus y square plus 4 actually. Then if you calculate the gradient normal, the normal is given by normal to phi is given by gradient of phi actually here. Okay, so it's given by gradient of phi, and gradient of phi at the point 1 comma 1 is equal to minus 1 by x square plus y square plus 4 into 2x I cap plus 1 by or minus 1 by x square plus y square plus 4 into 2y into 2y j cap. Okay, now you want this value at the point 1 comma 1. Okay, so at the point 1 comma 1, so if you keep this vector at the point 1 comma 1, so this gives you minus 1 by 1 plus 1 4 6 and 2 gets cancelled, so 1/3 x I cap minus 1/3 y. Okay, x is 1 and y is also 1, so 1/3 I cap minus 1/3 j cap. Okay, so this is what you have the vector. Now you want a unit vector, right? You can see the magnitude of x component of unit vector. So if you want a unit vector, how do you get this? So this is vector divided with magnitude. So therefore n cap, oh something got, okay, so let's see. So this implies n cap is equal to gradient of phi at 1 comma 1 by magnitude of gradient of phi at 1 comma 1. So this gives you minus 1 by 3 if you take common, I plus j minus 1 by 3 into this is root 2. Clear? So 1 by root 2 I cap plus 1 by root 2 j cap. So this is the unit normal vector. But why replace x dash? But why r square is equal to x square plus y square? Because this is asked as x component. They didn't ask you in the radial component. Correct? Otherwise I would have done the gradient directly. Dou phi by dou r I cap plus dou phi by 1 by r. अभी ओके ना? हाँ ठीक है, अभी ओके ना? ठीक है, so shall I continue? ओके ओके जी, ओके जी. Okay. It's okay now, guys. I hope it's okay now. Yeah. Okay. So let's continue then. Okay. There was this issue of power. I don't know why. There was a transformer beside my, not exactly beside, but some distance away. Morning that was blown up. So there was power fluctuation, and every time system is getting off. Okay. So, but if it gets off, just wait for 1-2 minutes. Okay. So that we can continue the things. So chalo. Now why I did not go for the direct polar coordinate gradient is because in the question it was mentioned that the x component, but if you do it in polar coordinates you will get the radial component. Again, converting a radial component to x direction and y direction components is difficult. Okay, so that's why I have done. Otherwise, see, gradient in polar coordinates is directly this: grad phi is equal to dou by dou r e r cap plus 1 by r dou by dou theta e theta cap plus dou by dou z of e z cap. So this is the direct polar. But if I do this, then I'll get the function, gradient function, in terms of this radial vector. Okay, radial component, theta component, and all, or at least the radial component in this case. So again, converting the radial component to x component and y component in terms of ij is what you should do here. Okay, so instead of that, you change the function.